Okay, good morning. Welcome back, everyone. I hope you're well. So let's just get started. It's been a while since the last time, it's nearly a month. And last time during the two lectures together, we talked about R and a little bit programming, and we introduced the interface of RStudio. We talked about data type. So something like scalar, vector, matrix, array, data frame, list. That's the most important one. Data frame and list, these two. And within each data type, for example, we have a matrix, and within each cell, it can be a number, it can be floating point, it can be integer, it can be a character, a letter, it can be a logical variable, true or false, and there are some special values as well. For example, NA, not available, or infinity, INF, or something like that. And then we moved on and we talked about a bit the control flow, if-else statement, and the for loop, looping from the first participant to the last participant, for example. And within that, we can also loop from the first child to the last child. So then in this case, it is a nested loop. And after that, we also talked about write our own function that is called the so-called user-defined function. To recall that functions, we could use the R built-in functions that's available inside R whenever you install it on your computer. And then sometimes those functions are not good enough. So you can search online, then find some external packages written by the community, and you can use the functions from the package. The third case is that even those external packages cannot be helpful in the particular data analysis case. And then in this case, you might just want to write your own function instead. So that's pretty much it. And we finished our last lecture by looking at a kind of real life example. So we had a two-choice task, if you recall that. So we present two stimuli to the participant, one blue and one yellow. And each of the two option or choice option is associated with a reward probability, meaning that one, if you choose it on average, it will lead to more frequent rewards, and the other one will lead to more frequent punishment or loss. We do not give this information to the participants, of course. So if the participants come in, they have to learn, they have to make a choice, they have to receive the feedback, and then they learn the updates, their internal valuation towards both or either of the two choice options. We did not really talk about the modeling part because that's the purpose or the focus of the second part of the seminar. We simply look at the data, right? So imagine that we have this task. Participants make a choice, receive a feedback, make a choice, receive a feedback. So we could organize our data in a way that it has each row is the child 1, child 2, child 3, and each column is data type. In terms of the first column can be the subject ID, the second column can be the child ID, the third column can be just the choices of the participants, 1, 2, 1, 2, AB, AB, left, right. And then the fourth column can be the feedback. So win, loss, reward, punishment, however you code it. And we read in the data from the local disk, from a text file into the R data frame. And then we did some analysis. And then moving from reading data from one participant, we then read the data from multiple participants. We wrote a loop, and then we concatenated all the data in a long format. And then in this case, we can easily take the advantage of R and the type of data frame to make further analysis. Okay, that's a kind of a summary of what we have done from the last time. And today we will switch gear a little bit. We will talk about probability. Pointer, yes. So the warm-up, sorry, the warm-up part, we have done it. So I hope you also follow me to think about what we have covered, what we have discussed from the last two lectures. And from today on, we will talk about something called probability. And then this is the building block of Bayesian statistics and cognitive or computational modeling in general. So this is another way to illustrate probability. So just for fun, probability is simply to assign numbers to a set of possibilities. And it has two important you have troubles with the audio? Can you stand, or shall I try to change it? Okay, use the headphone, I'm not sure. So let's see. Okay, I hope it's better. Wait a second. So can you still hear me now? Is it better or worse? Much better? Yes, okay, good, good. New lesson learned. Ah, interesting. Yeah, anyway, so since the word voice or the audio is better now, I will talk about probability. I guess it makes sense when I was talking about R, that voice is a little bit robot-like. And when I'm talking about probability, I guess I'm more human-like. So there are quite two important properties of probability. So one is that probability is not some random number. It is a number between 0 and 1, right? So from intuition, we know that probability is either 0% chance, so nothing can happen at all, or 100% chance, it will surely happen. So we know this probability by probably listening to weather forecast, for example, when we were kids. So the chance to rain tomorrow may be 70%. The chance to rain tomorrow may be 0%. The chance to rain tomorrow may be 90% when it's really cloudy and it is likely to rain tomorrow. So this number is lie within the range of 0 and 1. And another property is that, well, if there is an event, it has only two outcomes. The probability of each of the two or each of the many outcomes, the sum of it should be 1. So one simple example is coin flipping. So we flip a coin. It can either a head or a tail. And if this is a fair coin, then the probability to get a head and the probability to get a tail is 50% each of them. So we sum them up, 50% plus 50%, then it's 1, it's 100%. So that means the sum of it should be 1. Another case can be a dice. So if you throw a dice, we can get one of the 6 outcomes, the 6 numbers. And if suppose this is a fair dice, so then the chance to get each of the side facing up is 1/6. And if we sum them up, it is again 100%. So this is the probability. This is the property, the two properties of probability. And I think we know that already, right? It's as simple as that, but when we move to a little bit more complicated cases, it still obeys these two properties, but the situation can be a little bit complicated. And then I will introduce you that. Good. Any questions so far? I saw one. So are we working on any file today? No, it's more, we do not work on any programming today. We just basically listen to what I'm talking about probability, a little bit more conceptual. There will be some exercise, but it will rely on pen and pencil. That's enough. We don't have to do some programming. Good. The audio is worse again. This is too bad. Maybe that's the connection. Can you hear me now? Is that better or worse or stay the same? Shall I change? Same means not too good, right? Interesting. No. So if I use the Bluetooth. Yeah. Wait a second. How about now? Can you hear anything? Can you hear me or not? Is it better? All right. Okay. I use the cable now. I have the cable here, not the Bluetooth. Let's continue experimenting. So I talk about the two properties of probability. One is that there's a number between 0 and 1. The other one is that if we consider all those possible outcomes of a event and the probabilities, summing all the probability of each outcome is 1. Okay? So probability is used to express uncertainty. And then this is the way how we would like to consider probability. It's not only to describe our knowledge of how likely something is happening or something is not happening. So probability is very importantly to describe our uncertainty. So if we are talking about uncertainty, we are not only talking about one number. So probability, 90%, that doesn't mean too much. But if we say the probability of raining tomorrow is between 20%, ranging from 20% to 80%, it's quite long range. So you have quite some uncertainty. It can be no rain, it can be rain. So if you know me, I like cycling, right? If I look at the forecast of the weather and if I see the range of a raining probabilities is between 20% and 80%, maybe I'm not going out because it's quite unsure. What is sure is that if I know the probability of raining tomorrow is like between 20 and 30 or 35, then I'm thinking that maybe this is kind of, there's only a narrow range. I think even though there's some possibility that it will rain tomorrow, but the possibility is quite low. So you see that the range is narrower. On the other hand, if the probability of raining tomorrow is between 75 to 95%, then I'm definitely not going out because I'm sure, quite reasonably sure that there will be some chance of rain tomorrow, okay? Good. So let's see some examples. So when we were talking about probability, there are two types of probability. The two types, they depend on the type of the events. So if it is a coin flipping, we only get two possible outcomes. It's either a head or a tail. If we throw a dice, there are only 6 possible outcomes. So this is a discrete event. The event can be just 1, 2, 3. So discrete numbers, integers, like integers. Another type is when the event is continuous. And I will first tell you a little bit more about discrete events, and then we will spend some time on the continuous events. So when this event is discrete, the term to describe probability is called probability mass or probability mass function. So in this example, as shown here, assume there is kind of the paper pen test. And I give you 8 questions in total. There are 8 questions. And then you give some answers, multiple choice, for example. So there are only 9 possible outcomes. It can be that nobody, so there are let's say 16 people, let's say 20 people in this classroom. It's possible that none of them get any correct answer responded. So here, another extreme is that every 20 people in this classroom gets every question answered correctly. So 8, okay? So 7 means that many people answered 7 out of 8 questions correctly. So here means 6 out of 8 questions answered correctly. And then here, what the plot shows is the frequency. So in total, we have 20 people, let's say, and then let's say we are lucky, so nobody is really getting all those answers wrong. And then there's one person only answered 1 question correctly out of 8, and then more people answered 2 questions correctly out of 8, and then here 3 questions out of 8, and the majority of the 20 people in this classroom answered 6 out of 8 questions correctly. So this is probably just an easy way to show the distribution of the performance. I give you 8 questions and you give me the answer, either yes or no. I take a summary, I take a frequency plot, and I divide the frequency by the total number of questions by 8. So here, then I get this frequency versus the total number of questions plot, then that we get the proportion, right? If we divide the frequency by the total number of questions, we get the proportion. So here, this plot simply shows the proportion. And this is already a probability mass function. And if you could imagine, there are only these 9 types of outcome from 0 to 8. And if we take the sum of all those bars, we take the number of here, this vertical bar, we take the number of this vertical bar, we take the number of this vertical bar. We sum all those 9 vertical bars together, we sum those numbers together, and we get 1, right? This is something quite straightforward and easy to understand. So what is new here? There's nothing new from the plot. There's nothing new from how to calculate, how to get this plot. So what is new a little bit is that probably for a few of you, you have never heard about a term called probability mass. So here, just to remember, when we are talking about discrete events like coin flipping, like dice flipping, here this term to describe probability is called probability mass function. Good. And it gets a little bit more complex when we are talking about continuous events. So here, instead of calling it a probability mass function, we use the term called probability density function when the event is continuous. And there are not 1, but 2 types of probability density functions. One is called the PDF, the other one is called the CDF. The PDF is now the file extension. Here, the PDF means the probability density function. And the other one is called the cumulative distribution function or cumulative density function. Pretty much the same thing. So here, even though I tell you there are 2 kinds of density function, these 2 kinds of density function are in fact related and they are convertible. You can translate from the PDF to the CDF. You can also translate back from the CDF to the PDF. So let me give you one example. So here, what I'm talking about is still quite abstract. It's a little bit vague. You have no idea what I'm talking about if you have never heard about PDF or CDF, unless you read a book. So here, let's say we have a simple normal distribution, like a standard bell shape. And here, the mean of this normal distribution is maybe 68, roughly. And the standard deviation, maybe 2. I'm not just made up. And so what we can do now is to imagine
how this curve meets the two properties of probability. So we know that probability, it is a number between 0 and 1, and the sum of all the possible outcome is 1. So those are the two properties I described at the beginning of this lecture, and how to express these two ideas under this continuous distribution shape. So this is continuous, and I can tell you, so what is 1? So what is the sum of 1 is the entire area under the curve. So if you take the entire area under the curve, this is 1. So this is the way to satisfy one of the property of probability. And what is the number? How you get this kind of a number, the probability? So if you, for example, draw a line here, this is around 65. So what you can do is to calculate what is the probability that this kind of is below 65. So what is the probability to obtain something that's below 65, including 65, and everything below 65 is kind of what we're interested in. So then what you do is that you draw a line here, and then you take the area under the curve below or on the left-hand side of the curve, and then you calculate the number. So this is the number between 0 and 1. So if let's say the area under the curve at the left-hand side of this vertical line is 45%, and then the right-hand side, if you take the area under the curve in this white color, let's say it's 55%, and then those are the two numbers, 0.45 and 0.55. If you sum them up, they're 1. So this is the way to express the two properties of probability we talked about at the very beginning. Okay, good. And so what is the link between the PDF and the CDF? So if you draw a line again, but not this way. So if let's say the x-axis, let's say this x-axis here is exactly the same as here. So the numbers on the two x-axis, they are the same. And then if let's say I draw a line here, I'm interested in how much likely, or what is the probability that a number is below 65. So then, as I said, you draw a line here, you calculate the area under the curve, the blue color, and then you basically get a number of the area under the curve. And then you plot this number, the area under the curve, below 65 on a y-axis here. So here, 65%, 65, that's the number. Vertical line, they correspond to each other. And then from the top plot, you calculate the area under the curve below this line at the left-hand side of the line. Calculate the area, the blue color, and get a number and put the number here at the plot below. And then you do this cumulatively, constantly. So imagine there's a moving line. There's a moving line moving from the very left-hand side of the x-axis towards the right-hand side of the x-axis. So there's a vertical line that moves from the left to the right. And every time at very fine step, there's a line, you calculate the area under the curve at the left-hand side of the curve, and then you get a number, a value, right? An area under the curve. So you could imagine as the line moves from the left to the right, the entire area under the curve moves from near the beginning, because here there's nothing really under the curve. So the area under the curve moves from nearly 0 until here, 45%, for example. And if the line moves to the very right-hand side, the very right end of the curve, then the entire area under the curve is covered. So each time you draw a line here, you calculate the area and then you plot it at the graph below, and then you will get a shape like this. Okay? So you move a line, you draw a line, calculate the area under the curve, calculate the area, and then draw this line here on this plot. So then you see the idea, right? When this line moves from the left to the right, the area under the curve accumulates. In the beginning, it's a little bit little, and then as long the line moves along the line, as long as it moves, so the area under the curve increases. So it's a cumulative idea. Okay. And the y-axis of the graph below, it is between 0 and 1 because it's the cumulative probability. It can not be below 0. It cannot be it cannot be above 1. So that's the idea, right? That's the probability. It has to be between 0 and 1 under this cumulative density function. So there is a question. Calculating the integral of the probability density function and plot it on x. So it is calculating the integral from the top, but is to plot the result of the integral on the y-axis to convert from the PDF to the CDF. Yes, yeah, I tried to avoid talking about integral, but yes, if you're talking about that, yes, that is calculating the integral. Good. And then another visualization is, if you follow what I said, now we are moving the vertical line to somewhere around 70. So here is 70. We do the same thing. We draw a vertical line. We calculate the area under the curve. We calculate the integral between negative infinity until 70, right? So this is the range of the integral. And then we calculate it. And then this number is here. And then we plot this line here. We put the dots. And then we just get the cumulative density when x is 70. And then the cumulative density is here, I don't know, 80, 90, something. Yeah, probability percent. Good. So this is the relationship between the probability density function, the PDF at top, and the cumulative density function at bottom. So they're related. So I talked to you about the y-axis of the CDF. By definition, it has to be 1, right? That's the probability. You accumulate it, and it can be 0, but maximum is 1. It's 100%. So, but what is the y-axis on the top panel? So here, I didn't really give you the y-axis. So what is that? That is something arbitrary. So you can imagine that, so we have a normal distribution, we have a curve. We know that the entire area under the curve is 1. So then that means if the curve is very narrow, then it has to be high, it has to be sharp. Another scenario is that if the curve is a little bit short, is a little bit flat, then it has to be wide, right? Because there is a constant number. The constant number is that the entire area under the curve is 1. So that's the volume. That's the volume is 1. So you can also imagine, let's say we have a cake. The volume of the cake is fixed. We cannot change the volume of the cake. So if we want the cake to be tall, then the entire space, it has to be quite small, right? But if we want the cake to be a little bit big, in the sense that it's a little bit wide, then the cake has to be short. So to keep the volume constant, that's something we learned from physics, right? So the same idea applies also here. So if the curve, the distribution, the PDF is sharp and narrow, and then the y-axis can be actually pretty large. It can be above 1, honestly, because that's a relative density. It doesn't really give you too much absolute information. That's a relative density. We know that the value on this point is larger than the value of this point. But then we cannot say the probability of this point is correspond to the value here. It is because if we draw a line here, let's say here 60. If we draw a line here, I ask you, what is the probability of being 60? So the probability of being 60 in theory, it's 0. So why is that? Because there are two intuitions. So one is that we have an outcome. The outcome is 60. So that's the denominator. So same idea as we applied before for this discrete events. So on the numerator, we say 60, that's the numerator. And denominator, so we have to consider all those possible outcomes. Well, you know that this is a continuous number. From negative infinity to positive infinity, everything is possible. So then this denominator is like infinity, right? If you divide one number by infinity, then you get 0. So here, the probability of being exactly 60 is 0. So then another idea, if you can say, if you can imagine, is that if you draw a line here at 60, and if you move the line either left, right, or either leftwards or rightwards, even if you move only slightly, so the line can not be 60 anymore. It can be 60.1, 60.01, 60.001. So then the line is very thin, right? You cannot really calculate like the area under the curve of a very thin line is 0. So what you can do instead is, as I showed you already, you draw a line here, then you calculate the range, the area under the curve within the range. So if you calculate here, we draw a line, we calculate the probability of being smaller than 65. We can also draw two lines here. We draw one line here, 60. We draw another line here, 65. Then we could calculate the probability being larger than 60, at the same time smaller than 65. So in short, for this PDF, if we want to calculate probability, if we want to calculate the probability of an exact number, it's 0. What we can do instead is we calculate the probability within the range. So two possible scenarios. One scenario is to draw one line. We calculate either the probability above this number or below this number, as shown here on these slides. Here, another scenario is to withdraw two lines, and then we calculate the probability within this, in between these two vertical lines, and we can also actually calculate the probability larger than the upper end and the smaller than the lower end. That's also possible. But the idea is the same. When we draw a line here, we calculate the probability within the range using the PDF. So calculating the probability from the CDF down below, that's straightforward because the y-axis it indeed refers to the probability as I showed you, because that's the integral calculated from the PDF. Okay, there's a question. The y-axis is not scaled from 0 to 1, so it cannot be a probability. Are you talking about here or here? If you are talking about the CDF here, it is 0 and 1. So maybe there's some illustration thing. Yeah, I found from the internet. You're right, it's not exact, but it has to be from 0 to 1. Yeah, yeah. Yeah, so blame the website here. Or from, well, there used to be, they're usually good. I mean, I don't know. So here, it has to be 0 here, down here. It has to be 1 here, okay? It makes sense to interpret the y-axis of the CDF. So what I talk about quite a few minutes is that it doesn't make too much sense to interpret the y-axis of the PDF. And that's why I didn't even plot the y-axis here on this graph. Good. Any questions? Yes. So here it says, the probability is the area under the curve of the PDF up until a certain point on the x-axis. And then that's the CDF. You can calculate this way, the CDF. Yeah, that's right. So here it says, imagine the PDF that's very dense in the range of expected value. So that's the case I said for the PDF, something here. It can be very sharp and very tall, very high. And then in this case, the y-axis can be even 100, doesn't matter. So here, the y-axis of the PDF, you cannot really interpret it. That's the relative density. If you do want to interpret, you can say that's the relative density, but that's not the probability. So here, that's the point, right? So if you see the PDF, the graph, if you want to get the probability, you have to draw a line and then calculate area under the curve within some point, within the range, in between the range, or up until a point to get the probability. But the y-axis itself, it is a relative density. Doesn't make too much sense to interpret it. So high is high, low is low, yes, of course, but then that doesn't mean a probability. Here, easier case is CDF, right? The y-axis, it indeed means probability. So you can interpret like usual. So that's easy. Yeah, I guess that makes sense. So let me summarize. We had quite a long discussion. So let me go back to summarize from here. It's easier. So we have two types of probability functions. And these two types, they depend on the type of the events. And when we were talking about discrete events, in this case, like coin flipping, like dice flipping, like in this case, throw a basketball even. So in this kind of cases, the events is discrete. And then we will use a term called probability mass function to describe probability. And what gets a little bit trickier is when we have these, rather than discrete events, when we have continuous events, we use two subtype of probability functions to describe continuous events. And both of them, they are density functions. So one is called probability density function, the PDF. The other one is called the cumulative distribution function or cumulative density function, the CDF. They're not two random terms to describe a probability from this different perspective. Well, they are describing probability from different perspectives, but they are not random, they are not unrelated. Instead, they are related and they're closely related. You can calculate from PDF to CDF, you can convert it back to calculate from CDF to PDF. So one simple example is, as shown here, a normal distribution. So what we are familiar with already is the bell shape. The bell shape here, like here, this nice curve, it is a PDF. So if you go to the normal distribution of Wikipedia, it actually shows you the function, the equation, the formula of a PDF, and also shows you the formula of a CDF. So how these two are related? So intuitively, if you draw a line here, you calculate the area under the curve up to this point, and then you plot it here down below. So then that's the relationship. The interpretation of the y-axis of the CDF, that's straightforward. That means probability. Yes, it does. But the y-axis of the PDF function is quite arbitrary. So it is only a relative density. It doesn't mean probability. But what if you want to have a probability from the PDF? So draw a line here. As I said, calculate the area under the curve up to a point or in between two points, two cutting points. So similar idea, when we move the line from here, 65 to 70, then the area under the curve increases. So then you'll see the idea of this cumulative, accumulating idea. So that's how it is named cumulative density function. Good. so that you still memorize what we have discussed. So there is another example. So suppose that we have a set of numbers from 1 to 100. So this should be the same size, but doesn't matter. So let's say there is the set of 100 numbers. If we want to randomly draw a number from this set, let's assume the probability of getting each of the numbers is the same. So then we could easily derive that the probability of getting each of the 100 numbers is 1 over 100, right? So here is 1 until 100. Here, that's the probability of getting this number. So it is 1 over 100. And another property we describe is that this sum, this overall summary of all these possible outcomes, the probability, the summary of the overall probability of each outcome is 1. So if you sum them all together, it's 1. You can also plot this. So on the x-axis, here 1, here 2, and here is 100. So on the y-axis, this is 1 over 100. And if you sum all those 100 numbers together, that's 100%, right? Good. And another example is for a continuous events. And let's talk about something a little bit more concrete. We can talk about body height. So the body height. Let's assume here this average body height of the Austrian population is overall set. And then let's say we have kind of a normal distribution shape, because we kind of know that the overall distribution of body heights can be a normal distribution. So maybe on average, here is between, I don't know, 170 to 180. I'm not sure, I'm just guessing. So anyway, so here this is the overall distribution of the heights. And then if we want to calculate the exact probability of one person being 180, so 1 meter 80, it is 0. Because if we draw a line here exactly over 180, then there is no area under the curve you can really calculate. You can even say, because the numerator is 180, the denominator has to be all those possible body heights. It can be 181, 182, 181, 180, 111. So that's everything's possible, right? Because this is a continuous event. And what you can do instead is to draw 2 lines here, for example, here and here. Let's say we're interested in the probability of being higher or taller than 175 and shorter than 185. And then in this case, we can then easily draw 2 lines and we calculate the area under the curve in between the 2 lines, as shown here in this shaded area. Good. Any questions up to this point? No? Good. Yeah, good. This is a little exercise and you can actually do it at home. So I talked about PDF and CDF, and those plots look nice, and how to get it in R. And in R, for any distribution, you can add a letter in front of it, like a prefix. So let's say norm, this NORM. Let's say norm is for normal distribution, okay? And then you can add a letter D in front of it. So D norm, this implies a PDF. If you say a P norm, this implies a CDF. And then you can also do 2 others. So one is Q norm. So then in this case, you can calculate the quantile of a normal distribution. And then if you want to know a little bit more detail, so the Q norm and P norm, that makes sense, right? P and Q, right? So the P norm and Q norm, they're actually the inverse function. And I can show you later on the graph. And the last one is the random number generation. So if you, for example, are interested in to generate 100 random numbers from a standard normal distribution, the mean is 0, the standard deviation is 1. So you can use R norm to generate random numbers. Good. So in this example, I show the plot of a standard normal distribution. So 0, 1 case, D norm like this, that's the PDF, right? Probability density function. So here is the cumulative density function, the CDF. And then this one is the Q norm, the quantile. And then the last one is a randomly generate 1,000 numbers from the standard normal distribution. And then I plot the histogram. So it shouldn't be surprising that here this shape is pretty much the same as the theoretical distribution, the PDF. A little words on the relationship between the P norm and Q norm. The CDF and the quantile is, if you imagine there is an identity line. So here, 45 degrees. If you draw a line here, and then along this line, you draw a symmetrical counterpart of this curve. There is a line here, and then you draw the symmetrical counterpart of this curve, and then you will get something like this, right? Then that's this one. So then that's the Q norm, that's the quantile. So then here, the P norm and Q norm, they are the inverse functions. So if you're interested in. Good. And any questions? So what you can do at home is that you do the plots of the D norm, the P norm, the Q norm, and the R norm, not from the standard normal distribution. You can do whatever you like. You can say normal 10, the mean is 10, and the standard deviation is 5. And then you can just simply draw these 4 curves according to whatever normal distribution you are interested in, just to have a test, to have a taste of how this curve, the plotting works. Here, I didn't really use ggplot. I think I just used the base R plotting function. So don't have to look fancy. You just plot it to have a feel of the 4 curves. In particular, these 2, right? The relationship between the CDF and the PDF. Ideally, you plot the PDF on the top, here on the top, and this one on the bottom, and then you will get the nicer correspondence like I showed you here. Good. So far, we talked about the probability of only one event. So coin can be a head, can be a tail. The height, the body height can be 180, 181. So this is one type of event, right? But in real world, there are quite complex situations where we do not have one type of event. We might have multiple events. So then in this case, there are a few different new concepts or new terms that could help us understand the probability of multiple events. And here the most important ones are the joint probability, the marginal probability, and the conditional probability. A little bit mathy-ish, but not really, but I can show you, I can walk you through slowly. So here, let's say, suppose we have 2 types of events, A and B, just some random events, right? Random events, A and B. And the probability of both of the 2 events happening, this is then called the joint probability, because the 2 events, they jointly happen together, or not happen, doesn't matter. So these 2 events. And then the order doesn't matter here. The probability of A together with B is the same of the probability of B together with A. So this number, the order doesn't matter. The order doesn't matter, right? And putting that into a concrete example, we can say there's one event is raining, and another event is cold, is being cold. And then the probability, the joint probability of raining and being cold is simply the probability of raining and at the same time the probability of being cold. Okay, good. Another probability here is marginal probability. Marginal probability maybe is a little bit new to you. So the marginal probability basically means the probability of one event irrespective of another event. So here, what I can show as one example is that I'm interested in the probability of rain. When there is a possibility that there is another event, cold or not cold. So here I have to tell you a little bit more. So in the sense that if we are talking about only one event, so something like the coin flipping, we do not have to care about who is the president of the United States, right? We just talk about the probability of getting a head or getting a tail. So they're not really something related. So we just only talk about the probability of getting head or tail. But here, why I have to decompose the probability of rain to something like here, because there is another event. So the other event is the other event is cold. But how to decompose? It's actually straightforward in the sense that if I'm interested in the probability of rain, then I don't care if it's cold or not cold. So then it's basically a summing up of probability rain when it's cold and the probability of rain when it's not cold. So then if you understand this, you can actually make sense of the probability of the coin facing up here when the president of the United States is somebody and when the president of the United States is somebody else. So it doesn't matter. So I don't care who the president is, and I just only interested in the probability of the coin facing up or tail, facing up or down. So that's the marginal probability. So probability of one event irrespective of another. And why it is called marginal probability, there's kind of a historical reason that I can show you later during our exercise, small exercise. Good. And then the third concept here, was a term that describes the relationship between multiple events A and B, is called conditional probability. And this is something we will see very often throughout the entire seminar until the very end. So here it's written like this: P in the parentheses, A with a vertical bar and B. And it reads like the probability of A given B. So the right-hand side of the vertical bar, that's the condition. And given this condition, what is the probability of A? So you understand this way. So you go from the very right-hand side to the very left-hand side. So the B is there. Let's assume the B is there, and when it's there, given that, conditional on that, what is the probability of A, right? P of A given B. So it also means the event B is fixed. It's there already, and it's there. We are not interested in anymore. It's there, and we just are interested in when the B is there. When it's there already, conditional on that, what is the probability of A? And there is a very interesting relationship of everything I talked to you. So there is a relationship between the joint, the marginal, and conditional probability. So the relationship is that here, the joint probability equals the multiplication between here, the conditional probability, and here, the marginal probability. It's still a little bit abstract, and then maybe it's getting better when we are looking at the example down here. So again, the same example, rain and cold. The probability of raining and being cold, these two events, right? This is the joint probability, equals to the multiplication of here, this conditional probability, and a marginal probability here. So how to read this? Again, you could read this equation from the very right-hand side to the very left-hand side. Here I say, first of all, what is the probability of being cold? And then when this is known, we do not have the uncertainty anymore. So then this code becomes the condition. And conditioning on that, on being cold, then we calculate what is the probability of rain, okay? There's a comment, it says, I thought that P of A and B equals P of A multiplied with P of B. It is true when A and B are independent. And here, if they are not independent, it can be a little bit complicated. Yeah, you're right. So let's comment on that. If events A and event B are independent, if they are independent, so then this conditional probability just equals P of A, because it doesn't really rely on B. Conditional on B, whatever, I don't care. So conditional on B to calculate P of A basically equals P of A if they are independent, right? So here is a more generic way to express this relationship. And then when they are independent is kind of a special case. Make sense, right? I guess. Good. Let's do some mental calculation. Well, you can use pen, paper. So this is a way to have a better understanding of the three probabilities I described. Marginal distribution, marginal probability, sorry. So marginal probability, joint probability, and conditional probability. We talk about only three types of probabilities, okay? And we are only talking about here as a discrete events, because it's easier to understand to grasp at the beginning, and then extend our knowledge from discrete events to continuous events. Same example, there are only two events. One is cold, here cold, the other one is rain. So this event is like a coin flipping. It means it can be, it could have a few possible outcomes. So flipping a coin, we can have a head, we can have a tail. So here rain means it can be rain, it can be no rain. So there are two possibilities, rain, no rain. One here means yes, zero here means no. So rain and no rain. Cold, same idea. So here one means being cold and zero means not being cold, okay? And then we could construct a table, a 2x2 table like this. And then we could just randomly or arbitrarily give a few numbers given our knowledge about the world, for example. We could say the probability of being rainy and being cold is quite likely altogether. So then we say, maybe 50% of the chance these two happen together. And we say when it's not rain, when it's not cold, this could also happen at a relatively higher chance. So when it's sunny, no rain, and not cold, like today, for example, we can say 30%. And we can say the probability of being no rain but cold. So like cloudy day, no rain, but just cold, let's say just 10%. And another one is when it's raining but not cold, it happens, but maybe not so frequent, also 10%, okay? So this is just some arbitrary numbers. We can just imagine, makes a little bit sense, but usually not really. And here, this is only a simplified example of the word cold, no cold, rain, no rain, okay? So we have those four numbers filled in this table. Okay, good. Question number one. We have four numbers here, 0.5, 0.1, 0.1, 0.3. So they are, what are they? Are they conditional probability? Are they joint probability? Are they marginal probability? So you can just write down in the chat box. I think, I only have this chat box. What are they? Yeah, great. So few of you wrote down joint probability. Yes, they are joint probability because they describe the probability of some events belong to each of them happening together, right? So here, this 0.5%, 50% probability describing raining and being cold. So this is a joint probability because here and here they happen, and then this is the joint probability. They happen together. What is probability of raining and being cold? They happen together. That is a joint probability. Okay, good. So here is a joint probability, and it can be described in this way. So for example, if we're interested in the probability of x being 0 and y being 1, so here, x0, 1 here, and then the joint probability, not surprisingly, we go to this cell in the table, and then we get 0.1, right? So we could generalize this formula a little bit. We could use this way. So first of all, forget about the sum part, and then here, this is the joint probability, okay? And then in our simple case, we only have 4 possible outcomes, and then the sum is 1, okay? So this obeys the property of probability we introduced at the very beginning. Okay, then we move down to marginal probability, and then to calculate marginal probability, I remind you again the definition of marginal probability. That means when we have 2 events, A and B. So marginal probability means the probability of event A irrespective of event B. So it doesn't matter it's cold or not cold. I'm just only interested in the probability of being rainy or not being rainy. So I already give you the hint, and now you can try to do some calculation. So I'm asking you here, what is the probability of being cold? It's quite straightforward right now, right? Yeah, it is. So it is 0.6. The probability of y equals 1 means here, in this example, the probability of being cold is to sum up these 2 numbers. And then you can write down a 0.6 here. So why is that? It is because the probability of being cold is the probability of being cold when it's raining, and then the probability of being cold when it's not raining. So I don't care if it's raining or not raining. I'm just only interested in the probability of being cold. Then I have to consider all the possible outcomes of here, this event, and then I sum them up, irrespective of the other events. I'm only interested in here. So then, as I showed you, I highlighted these 2 numbers, 0.5 plus 0.1, then it gets 0.6. So imagine you could write down the 0.6 here, right? You could also write down here 0.4. You could also write down here 0.6. You could also write down here 0.4. So what you get is some distribution, some probabilities here, and then these 4 numbers, imagine there are 4 numbers here. So these 4 numbers, they appear at the margin of a table. So that's the historical reason why it is called marginal probability, because it appears at a margin, at the marginal place of a table. When the ancient statisticians are talking about discrete events, they do this way. They make a table, they write down the marginal distribution, and then they have to name it. Well, they say, okay, marginal distribution or marginal probability. Okay, good. Another calculation is quite straightforward again. So if I'm interested in the probability of no rain, So then you can write down now already in the chat box if you want. So if I'm interested in the probability of knowing here, so then I don't really have to care if that's code or not code, okay? So then I get these numbers, and then these two numbers, I can sum it up, the same idea, right? The probability of x being 0, irrespective of y being 1 or y being 0. So then I get these two numbers, I sum it up, and I get 0.4. So imagine here we have 0.6. Imagine here we have 0.4, we're calculating from here. And then these two numbers, they also sum up to 1. So the sum of the marginal probability, they are also 1. This is not coincidence. It's by design. It is the way it is. So it's distribution. It's not distribution. It's probability, and then they have to sum up to 1. All right. And to generalize the idea of marginal probability, so here I'm interested in the capital X equals to small x. Then I have to calculate x equals to small x, and then irrespective of y. What does it mean to be irrespective of y? Then that basically means you have to calculate the joint probability for each possible outcome of y, and then sum it together. So here, let's go back. If I'm interested in the marginal probability of y being, not y, sorry. If I'm interested in the probability of x being 0, then I take the sum of the joint probability of x being 0, y is 1, x being 0, y is 0. So those are the possible outcomes of y. And I take the sum. So I take all those possible y. And then when all those possible outcome of y is considered, we sum them up, then we can ignore the, we can get rid of y, right? So then we can say just marginalize y. Good. The third one is conditional probability. We can again use the same table here. We use the same table because if we are working on the same example, we can have a better understanding of what is going on, right? Of the different probabilities. Okay, I highlighted already. So I'm now telling you, I'm interested in the probability of y being 1 given x is 1. So what that means, I'm interested in the probability of code being code given that it's raining. I think this highlighting is a little bit confusing. But anyway, so here, I'm asking the question again. So you can just ignore these highlights. Well, you can ignore the highlights. It's wrong. So I am interested in the probability of y being 1. So here, y being 1, given that x is 1. Given that x is 1. So what is the probability of that? It's a conditional probability. Condition is x being 1. And then conditional on that, probability of y being 1. Given that it's raining, I'm interested in what is probability of being cold, okay? I saw a few responses. One is 0.5, another one is 0.5 over 0.6. And then Jakob seconded that and he changed his mind. Okay, any more? Any more active listeners? Or you all agree with that? I guess you do. Yeah, cool. That's nice. Awesome. So it is 0.5 over 0.6, and then it's 5 over 6. So why is that? It is because if I'm interested in the conditional probability, so here when x equals 1, so then I basically only focus on this column. this column, x being 1. I will change the highlight later. So I focus only on this column, x being 1. And then out of this column, what is probability of y being 1? So then I go here, I go to this cell. So then that basically means what is the relative probability of this one as opposed to the entire sum of this column. So then basically here we use 0.5 divided by the total sum of this column. Right, make sense? So that's the conditional probability. You have to fix this one first. So when x equals 1, we only look at here, this column. And then we go to this cell to calculate what is the conditional probability. So then to make it a little bit more complicated, so here is kind of a generic formula or equation of conditional probability when we have two events, x and y. So probability of capital X equals to small x, given that capital Y is smaller, it is the small y, is on the numerator, the joint probability over the marginal probability. Do you see that here? The numerator is a joint probability. The same, right? The numerator here, this is a joint probability. The joint probability of x is 1 together with y is 1. And the denominator, quite interestingly, it is actually a marginal probability. So here, P of capital Y equals Y, you have to decompose it, that you have to expand it a little bit. So here, similar idea as this one, because here we focused on X and then here we focus on Y, in the sense that you calculate probability of Y being smaller y, irrespective of X. So then you consider all those possible outcomes of X, and then you sum it up. So here, when X is 1, well, this is kind of, that's why the reason I think I am confused. So if we are interested in here, then it doesn't matter here is if that here is code or no code. You just have to look at the column of one event, irrespective the column of another event. To make it easier, wait a minute. I think I have to change it now. Otherwise, I'm confusing you and myself. The easiest way is to do this, I think. And I do not have to change the highlights. I do not have to change the equation. Okay, that's easier, right? So when y is 1, so here when y is 1, I guess even nicer. When y is 1, then we calculate here the denominator, the marginal probability of y being 1. So then irrespective of x being reigning or no reign, right? This is the idea of the calculation. Good. Quick summary. So we spent quite some time on this concrete sample when we have two events. It's either a rain or no rain for event 1, or a code versus no code for event 2. And then we arbitrarily fill in a few numbers, and then all those numbers here, these 4 numbers in each cell in this 2 by 2 table, they represent the joint probability. And from this table, we can easily calculate the marginal probability by going to the margin and take the sum of here. And we go to the margin here, we take the sum of these 2. And then the marginal distribution, the marginal probability by definition means the probability of one event irrespective of another one. So if I'm calculating this marginal event, that means the marginal probability of y being 1 irrespective of x being 1 or 0. Doesn't matter, I don't care. I just only I'm interested in here. The marginal probability of y being cold here is 1. Similarly, I can calculate the marginal probability here irrespective of the value of y. And then thirdly, we calculate the conditional probability. So here, remember this expression. There's a vertical bar here. It reads like probability of event A given event B is fixed. So then if we are interested in this conditional probability, we go to this condition first. We go to this highlighted part, and then we calculate when x is 1, what is the probability of that? And in this case, it's 0.5 over 0.6. And then you can read here to get a better understanding. And quite importantly is to understand here, when we are calculating the conditional probability, in this case, the y-axis, there are two, not y-axis, there are the denominator, there are two events, x and y. So this is the joint probability. And then the denominator is the marginal probability of the condition, right? The condition. Here are the examples, calculation examples of discrete events. And we need to move to continuous events. And then this is a little bit interesting. So we cannot really make a table of continuous events, because if we were to consider all those possible outcomes of a continuous event, then that's infinity, right? So we cannot really make a table. It's not really possible. So what we can do is, like, for this univariate distribution, the normal distribution, we draw a curve. And then what can we draw for this continuous events when we have multiple events, continuous distribution? So what we do is that we draw also kind of a multivariate curve, or something like a shaded area, a cloud. In this case, this is a joint distribution. So here we say x-axis is just one event, event x, and y-axis is another event, event y. And then this joint scatter or joint shaded area that the contour plot describes the joint distribution of the two events. So that's the co-distribution of x and y. Good. And then if you look at, again, like the margin, if you look at the distribution of the x-axis, irrespective of another one, and then here, if you look at the distribution of the y-axis, irrespective of the x, so then you get a marginal distribution. The same idea, right? You are interested in one event, irrespective of another. So then in this case, you only look at x, irrespective of y. And here you look at y, irrespective of x. And then you get the marginal distribution. And here, when there are two events, it also appears at the margin, the place of the margin. Okay. And then the third one is the conditional probability. So here, this one, top left corner, that is the joint probability. And what it means to be a conditional probability, that means we fix one event, and then we look at the distribution of another one. So then similar idea, we fix for each line here, I conditional on y being this value, and then I look at the probability distribution of x-axis. So then here, this curve at the very top is the conditional probability of x given y equals this value. And if I move down to here, that's the similar idea. Here, that shows the conditional probability distribution given y equals this number. And same, if I go here, that means the conditional probability of x given y equals this, and so on and so forth, right? The last one basically means the conditional probability of this given y equals this, okay? And also recall the distinction between the CDF and the PDF. So here, this thing, this shape, or all of the shape, doesn't matter. So what are they? Are they PDF or CDF? Yeah, so they are, exactly. So they are the PDF, the probability density function. So there is a very simple way to distinguish a PDF or a CDF and a CDF. So distinguish the PDF from a CDF. So a CDF always increases because that's cumulative, right? So here in this case, it goes up and then goes down. So that cannot be a CDF. So that's a PDF. Make sense, right? Any questions? Any questions? Everything's all right? Good. Okay, cool. So let me just continue. We do have some time, and this one won't take too long. So we can just introduce the Bayesian theorem when we understand the three important distributions when there are multiple events. Let me just summarize again. So the conditional probability, the marginal probability, and the joint probability. Okay. So we start from here. We have the P of A and B and the P of B and A. They are the same. The order doesn't matter. I don't really care who happens first, who happens the second. I'm just interested in the joint probability of event A and event B. And we know that from the example above, we know that the joint probability of A and B can be expanded as this way. Okay. So idea same again. Read from the right hand side, and then we go from the right to the left. P of B is here, and then given B, what is the probability of A, right? This is the marginal probability. This is the conditional probability, and we do the same thing for this one. We say, okay, we change the order, so we change from A and B to B and A, and then we just write the same thing. The only difference is that we swap the order of A and B. And we know that here, these two are the same. So then we know that the right-hand side of these two equations, they also have to be the same because that's simply how it works. So then we get this equation. That's very nice. And then we can rewrite it. We can reorganize the equation a little bit. And then we get the so-called, the famous Bayesian theory. So we have this shape. So the probability of A given B equals probability of B given A multiplied probability of A divided by probability of B. So it's basically to describe a conditional probability by the conditional probability of the reverse. And then there's some terms that you have to consider. So that's it. That's the Bayesian theorem. So whenever you're interested in, whenever you forget maybe, and if you go onto the street and then somebody come to you, hey, can you write down a Bayesian theorem for me as well? I don't know why they do this, but there are some people that might just jump into you to ask you write down Bayesian theorem for that person. Well, you can forget, it's possible, but you never forget this, right? These two are the same. And then you can actually also easily expand the joint probability in the way of here, this product. And then you can easily derive this form. And then this is the Bayesian equation. You never get it wrong. Whenever you understand it, you never get it wrong. Good? So that's it. All right. So we can do some a little bit complicated. Not really complicated, just because there are more numbers, and then you have to use pen and pencil to do this exercise to finish up today. So this is a more generalized formula or example of discrete events. So recall the previous example, we have here rain versus no rain, here cold versus not cold. And then everything inside is a joint probability, everything at the margin, that's the marginal probabilities. Everything I write down is the same, okay? And in this case, we have more numbers. let's say we have a table of probabilities of two events. One is the hair color, the other one is the eye color. So hair color, these 4 outcomes from black to blonde, and then so eye color here from brown to green, okay? Similar idea in the sense that every number in this table, so here 0.11, 0.03, 0.03, 0.20, 0.14, so all those numbers are not surprisingly joint probability, right? Here 11% means 11% hair color being black together with eye color being brown. This number means 3% chance probability that hair color is blonde and the eye color is green. Okay, so all of them, if you want to calculate, they have to sum up to 1. They have to, right? That's the way it is. So you don't have to. So they do sum up to 1. And here, so each row, if let's say I'm focusing on this eye color being blue, and then irrespective of the hair color, doesn't matter here, black, blah, 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 red, blonde, then these 4 numbers, they sum up. If we sum them up, we get the marginal probability of eye color being blue, okay? We can also do the same for being brown, hazard, and being green. So all of these 4 values, they are the marginal probability. And these 4 marginal probability, if you do sum of them, they also sum up to 1. So that's focusing on the row. If we focus on the column, so if we focus on here, the hair color, and then irrespective of the eye color, I don't really care the eye color. I'm just interested in the probability of hair color being blonde. And then I sum up all these 4 numbers, and then I get a marginal probability of 0.21, okay? Good. Any question? Ah, yes, right. So there's a question that asks, what is A star? So A star means every possible outcome of A. So here, this A means it's either, let's say A is eye color. Here, this A means either each of the 4 of them. So here, A either means brown or blue or hazel or green. So here, A only means 1 possibility. Here, the A star means all of them. Because if you remember that this denominator, we calculate the marginal probability. So then we have to consider all those possible outcome of A. And then we take the marginalized probability, and then we calculate P of B. So here, this means P of B, right? Because the Bayesian equation here means P of B. And then to calculate P of B, we have to calculate the marginal probability of P of B. And then we consider all those possible outcome of A, and then we sum all those possible outcome of A up. We get the P of B, right? Make sense? Good. Yeah. So then we can finish our lecture by working on a small exercise. Yeah. So suppose that in the general population, the probability of having a rare disease is 1/1000. So we denote the true presence or absence of the disease as the value of a parameter called theta. and this theta only takes two possibilities. It's either a smile phase or a sad phase. Smile phase means there is no disease, and sad phase means there is a disease. The disease is there, present. So translating this a few sentences into a statistical language, that means the probability of having this disease is 1/1000. So there are a few assumptions. Let's say there's a test, like the test. There's a test for the disease that has a 99% of hit rate. Hit rate means when the disease is there, what is the chance to detect it, right? So translating this into a statistical language, that means given that the disease is there, and what is the probability that the test gives us a positive result? So here, this is a 0.99, given that assumption. Suppose number two, so not all the tests are perfect. They make mistakes, and sometimes they have a false alarm rate. So what is a false alarm? False alarm means there's nothing wrong, no disease, but then the test says you have this disease, unfortunately. So translating this into a statistical language, that means given this is a healthy person, and what is the probability of the tests given us a positive results? If that's 0.5, then that's, let's say here, this 0.05, right? So that's the false alarm. So now you have all those numbers ready. So if you have all those numbers at hand, you can actually answer a question written here. So suppose we just sample a random person from the population and we administer the test. And then the test result says you're positive. And then we can answer, we can calculate, so what is actually the probability that the person really has the disease? So translating the question into a conditional probability shape, we can say, given the test says a positive, what is the probability that the person is actually having the disease? So I can give you 5 minutes. I show you here. So all those numbers are there. And the hint to calculate this one, to finish up today, is go back to this example. Go back to this rain and cold example. So here, let's say, this is the disease, yes or no. So sad phase and happy phase. Here, that's the tests, either a positive or a negative result. And then not every number is available given the number I give you. But then you can calculate each of the cell. And then you can get, finally, what is the probability of having the disease given the test is a positive. So what is the probability of really having the disease given the test is positive? Okay. Do you want to do it or not? And let me know. You can also do it at home. But the idea is to write down the table, fill in all those numbers. And whenever you have those numbers ready, then you can easily calculate, you can easily answer the question. Okay, let's say 5 minutes, and use your pen and paper, and then you can calculate it. Okay. Yeah, I see that some people want to do it, some people do not want to, but just 5 minutes, okay? If you do not want to do it now, you can take a break. And then maybe just think about it. So think about what we have learned today. And for those who want to do it, now you just go ahead. And we come back in 4 minutes. Yeah, so for those of you who do not want to do this exercise now, you can just listen to me. Quick summary of what we have learned. So we talked about probability today. There are two important properties of probability. So the number has to be, the number of the probability has to be between 0 and 1, right? It cannot be negative, it cannot be 2, it doesn't make sense. So it's between 0 and 1. And the sum of all those possible outcome is 1. So then the sum up to 1 thing is quite also important. And then we move to specific type of events. Depends on whether the event is discrete or continuous. We have different types of probability function. If the event is discrete, we talk about probability mass function. And if the event is continuous, we talk about probability density function. And we are talking about not one, but two types of probability density function. One is the PDF, the probability density function, not surprisingly, and then the CDF, the cumulative density function. So the link between the PDF and the CDF is that if you draw a line on the PDF, calculate the area under the curve up to that point, and then you get the number on the CDF. And then you get the idea of how the cumulative thing works. You move a line from the left to the right, and then you get the increasing probability illustrated by the area under the curve. And then we move to the scenario when we have multiple events. And then we talk about only 3 types of probability. So one is the joint probability, and another one is the marginal probability. The third one is the conditional probability. Joint probability means the probability, the 2 or multiple events, they happen all together. Marginal probability means the probability of one event, irrespective of another event. So I gave you the example of 2 events, A and B, but let's say we have not 2, but 3 or 4 events. We have probability of A, B, C, D, E. And if I'm interested in the probability of A, then I will have to calculate the probability of A irrespective of all those possible outcomes of B and C and D and E. Just don't care them, irrespective of them. So then you get the marginal probability of A. You can easily generalize this. And then the conditional probability basically means you have some certainty already on one event. When that is fixed, you do not really look at the uncertainty of that anymore. So given B is there, and given B is there, what is the probability of A? So this is the conditional probability. So we used the rain and cold example to have a quite precise and concrete calculation of all the three types of probabilities: joint, marginal, and conditional. And then I guess after this calculation, you will all have a better understanding of the 3 types of probabilities. When it's easy, right? When easy means only 2 events, not 3, not 4. And lastly, we actually introduced quite straightforwardly the Bayesian Theorem, because that basically only calculates or describes a relationship of conditional probability and marginal probability. And the P of A given B equals P of B given A multiplied with P of B and of P of B, yeah, divided by P of A, yeah. I think I said it wrong. So P of A given B equals P of B given A multiplied by P of A divided by P of B. This is correct, okay? So this is the Bayesian equation. And we then move down to this final exercise to calculate this test results and presence or absence of a disease. There is a, yeah, okay, good. So then there's a comment. So Jakob says, is it okay to post what I'm supposed to answer? Yeah. Yes, go ahead. What's your answer of this exercise? Let's see. I will share the slides, don't worry. So this is the answer. So the idea is that you're getting, no, not really closer, kind of, no, right? So the idea is that I give you all those numbers. I only give you 3 numbers. Here, 1/1000. Here, that's the hit rate. Here is the first alarm rate. And then I ask you this question. First step, use Bayesian equation to expand it. Second step, calculate all those numbers, all those possible numbers in this table. Here inside the cell, that's the joint probability. Here in the margin, that's the marginal probability. So when you have all those numbers, you use the calculation. You do this simple calculation. Doesn't have to be simple, but you can just do it using calculator or whatever. And then you'll get this number, okay? So then we do have to stop. So any questions? Can I tell you a little bit more about the summer school? Yeah. So yesterday I sent you a link of a summer school, and it's quite important that you know this is online, and most likely it will be free, okay? So it is organized or initiated by a group of people in the community called Cognitive Computational Neuroscience, CCN. And then there are people from the US, from UK, and mostly from the US and the UK, I think. Also one guy from Germany. So the idea is that usually they organize summer schools like locally, physically somewhere. And this year, because of the current situation, and they move everything online. And then they expect a quite large audience. And I think they would expect 3,000 people. And the idea is that it will be divided into big lectures. So like this, you listen to some guys talking about something, and then you will be divided. You will be grouped into some small groups based on the interest and also based on expertise. And then you will really learn some practical knowledge about how to do different of models in Python. So first thing, they do use Python. So they will also share with you some resources, links to how to learn Python. Data camp, for example. You can also use that to learn R. I can also share you the link so that you can practice yourself. So use Python, and then the type of model differs a lot. So if you read the syllables, they have it already there somewhere. So cognitive model, the thing we will be talking about is only a small part of it, and there will be something else. For example, like really machine learning related topics like deep neural network, convolutional neural network, CNN, and some network science. If you see papers, there are some like nodes, like a network, and then to use this knowledge to construct the brain and also to construct anything. So people's political belief, right? You can use their political belief to construct a network, of the society, for example. This is also a possible way to use the model. Yeah, I guess that's pretty much it I can tell you for now. And I think they're also recruiting not only participants, they're also recruiting teaching assistants and also professors to teach. So they're really recruiting people from all the level. And I think if they do this subgroup thing, you as participants, because we're in Europe, and you will only be paired with a TA also in Europe because there is no time difference. Consideration in this case. So then you will work together on small projects and then to solve problems together and then really get some hands-on knowledge. So what I can tell you from my experience, not this one, but from experience before, is that I participated 2 summer schools related to, one is cognitive modeling. That's how I got introduced to that. And another one, I think is also, it's a little bit more generic, but more or less is about Python. I think it's pretty interesting. So you go there usually in the usual setup. You go there physically, and then you study together. You actually eat together. You just solve problems together, right? And you get this intensive experience, and then you kind of have to force yourself to do something that you usually do not do regularly on a regular basis. So I think that's a pretty good way to learn. And note that this one is free, I guess. If you're interested in this topic, then that you just go ahead and sign up. And one kind of a challenge is that it's pretty long. It's 3 weeks. So it's 3 weeks spending the month of July, I think, from 13th to 31st, if I remember correctly. So it seems like if you sign up, you will just have to dedicate yourself just every day. It's like a full-time job. So you will do some exercise from 9 to 5 or 10 to 6, whatever it is, but you basically have to work a lot. You can imagine that after that, it can be very rewarding, right? If you learn a lot from the three weeks of experience. And I think that they will also issue certificates so that you have something, a completion certificate. Maybe if you're lucky, you can also get ECTS translated from these hours, because this hour is quite extensive, intensive. You can have quite some ECTS, I think. Yeah, I think it's possible. Maybe ask the university if you do it. Yeah, that's pretty much what I know so far. And if you have more questions, you can just also email me. Yeah, I know 2 of the organizers, and then not really know, but kind of. So if you have questions, I can also ask. Oh, wait. So they will have an online Q&A session today or tomorrow or sometime at our time, 9 in the evening. I can send you the link. So they will have an online Q&A session. So if you have specific questions, you can also ask them, the organizers. They know the best, right? Yeah. Perfect. Any more questions? Yeah, so if you have to leave, you just go ahead and leave. And if you have no more questions, I guess we see each other next week. Thanks.